I'm going to call this video Variations on the Ideal Gas Law. So I'm going to do a sample problem for you, and we're going to change or put some variation into the ideal gas law. So first of all, the ideal gas law is PV equals nRT. And if you remember in the first video, I mentioned that an ideal gas is a gas in which the molecules don't attract each other and the molecules themselves occupy no space. So those never really exist, but real gases approach ideal behavior, particularly when the temperature is high and the pressure is low. All right, so we have 6.3 milligrams of boron hydride, and it's in a flask, and the flask is 385 milliliters. So just draw a quick picture. Here's a flask, and you got BH question mark. We don't really know what the formula is for that hydride, but we know it's a boron hydride. All right, it's in that flask, and we're trying to find the molar mass. Well, we know that, lost my connection there for a second. We know that the molar mass, we know that the number of moles, anytime you find moles, like for example, let me show you, suppose I had 36 grams of water, and I want to change that to moles. So we would put grams of water on the top, and we put grams of water on the bottom, I'm sorry, and 1 mole on the top. 1 mole is 18. So when you do the math, you have 36 times 1 and divide by 18. So in reality, what you're doing is dividing the mass by the molecular weight. See, 36 was the mass, 18 was the molecular weight, so we ended up with the mass divided by the molecular weight. When I was in high school, my high school chemistry teacher taught me this was the way to find moles, but I haven't taught you that way. I've taught you to use dimensional analysis, but ultimately what you're doing is doing 36 divided by 18, which is the mass divided by the molecular mass. So up here, instead of N, I could plug in mass over the molecular weight. Same thing as moles. See, this is that. Okay, RT and PV don't change in this variation. All right, so now let's solve this problem. We have 6.3 milligrams of a boron hydride. Okay, so the mass needs to be in grams like it was up here. So I'm going to change the milligrams to grams. Now to do that, you can use dimensional analysis. I'll show you right here. So 6.3 milligrams times, you put milligrams here, you put grams here, 1 is 1,000. All right, so 6.3 divided by 1,000 is 0.0063 grams. Molecular weight is going to be, I'm just going to call it X because we're going to try and figure out what that is. Right here, the molar mass. Molecular weight, molar mass mean the same thing. Okay, R, I'm not going to put R in because I haven't talked to you about pressure yet. So let's go back and talk about pressure. We know that the pressure is 11 torr. Now, the R values that I gave you were 0.08205 liter atmospheres over mole Kelvin. And another one was 8.31 liter kilopascals per mole Kelvin, but I'm going to go ahead and use this one. So that means I have to change my torr into atmospheres. So here we go. So 11 torr. Now you remember that torr is the same thing as a millimeter of mercury. We talked about how a barometer works. So you have a tube like that, you got mercury here, air pushes the mercury up the tube. The distance between the high point and the level inside the bowl is the atmospheric pressure. So in this case, it's 11 millimeters of mercury, or 11 torr. Once again, called torr because Torricelli is the guy that created the barometer. All right, and then we're going to change this into atmospheres because if I use this value, then that pressure unit is atmospheres, and they have to match. So 1 atmosphere is 760 torr. In case you're wondering how I got this relationship, you remember that we listed standard pressures. I'll put SP over here for standard pressure. So it was 1 atmosphere. It was 760 millimeters of mercury, or 760 torr. It was 101.3 kilopascals. You know, you may be familiar with the kilopascals are very dangerous pascals, the kilopascal. That was just a joke. All right. So then there's also 14.7 psi. So those are all standard pressures. We've done those in previous videos. So when you actually do this math, since that's a weird, not a whole number, I'll have to whip out a calculator here. So I have 11. And by the way, Sophia Nicholas's birthday, it looks like, is coming up. So 11 divided by 760 is 0.0145. atmospheres. All right, so we'll plug that in for P, 0.0145 atmospheres. Okay, volume. In volume, and I told my chemistry classes I'd be online at 10:15, so I put a reminder on my phone. The volume in this case is 385 milliliters, but we can't leave it in milliliters. We have to change it in liters because the units on R are liter atmospheres. So 385 milliliters times milliliters on the bottom, liters on the top, 1,000. You see through my advertisement here. So 0.385 liters will be our answer for that. So 0.385. Let's go ahead and move this calculator off to the side. All right, so 0.385. All right, now R, we decided we're going to use this value for R, so I'm most of the time you'll see people abbreviate this to 0.0821, so I'll do that, and that's liter atmospheres over mole Kelvin. And then our temperature has to be in Kelvin. This is 25 C. Remember that to get it into Kelvin, you have to add 273. So 25 plus 273 is 298. So 298 K. All right, so what is canceled? Let's see here. I've got my problem set up. We notice immediately that Kelvin's cancel. All right, so I'm going to combine some terms here. Oh, I didn't put this as liters. Okay, I'm going to combine these two terms, 0.0145 times 0.385, 0.00558. And that's liter atmospheres equals. I'm going to multiply these three numbers, 0.0063 times 0.0821 times 298.154. Now you notice Kelvin canceled, but nothing else canceled. So that is going to be gram liter atmospheres over moles. And I still have that X on the bottom. I'm trying to solve for X because that's a molecular weight. So what do you do next? Well, this is an area that I'm going to put a box around this so we can highlight that area. So in algebra, you got to be aware that you need to clear your denominator. Remember, this is numerator, this is denominator. We need to get this X out of the denominator. So how do you do that? Well, there's a basic law about equations that if you multiply both sides of the equation by the same thing, the equation is still true. As long as you do the same operation to anything, as long as the operations are the same, you can do any operation to both sides and the equation is still true. For example, 2 equals 2, correct? All right, what if I multiply both sides by 3? So multiply by 3 times 3 times 3. So now I've got 6 equals 6. Is that equation still true? Yep. What if I took away 2 from both sides? Minus 2 minus 2. Now I got 4 equals 4. Is that true? Yeah. So as long as you do the same thing to both sides of the equation, what if I divided both sides by 2? Divide by 2, divide by 2. So now I've got 2 equals 2. Is that true? Yeah. So as long as you do the same thing to both sides of the equation's still true. So in this case, I want to do something to get rid of this x. Since I have this divided by x, if I multiplied by x on both sides, the x's over here would cancel out, and I'd have x times 0.00558 liter atmospheres, okay, is equal to 0.154 gram liter atmospheres per mole. So now, how do I solve for x? Well, we're going to divide both sides. We're going to do the same thing to both sides of the equation again, but I need to get rid of this number, and I need this x to be by itself. So I have to divide by the number that's with the x, 0.00558 liter atmospheres, divided by 0.00558 liter atmospheres. I'm starting to run things together a little bit. So these are gone. So x is equal to whatever that divided by that is. So let's do it. 0.154. I'm going to divide that answer I had previously by 0.00558. So it's 27.6. Let's look at our units. I'm going to separate out the units and show you real quickly how the units cancel. So I have liter atmospheres per mole divided by liter atmospheres. So I can put that over 1. When you divide fractions, you multiply by the reciprocal. So I would have liter atmospheres per mole times 1 over liter atmospheres. And look. You know what? I forgot about up here. This was gram liter atmospheres per mole. I forgot to set that unit out there. I'm sorry. But there it is. Gram liter atmospheres per mole. So this was gram liter atmospheres per mole. Then liter atmospheres cancel, and what I'm left with is grams over mole. And grams over mole are the units of molecular weight, or molar mass. You just add up, that's the molar mass. There's this many grams in 1 mole. So now the next question asks us to find out which one it was. Was it BH3, B2H6? So if we go over here to our trusty website and go to a periodic table, whoops, can't do that. And go to a periodic table. There we go. If you look at boron, it's 10.8, right? 10.8. So if you look at our formula weights, this is 10.8 plus 3. That'd be 13.8. Whoops, 13.8. This is 10.8 times 2, which would be what? 21.6, wouldn't it? 10.8, 10 times 2 is 20, and 0.8 times 2 is 1.6, so 21.6 plus 6, that would give you what? 27.6. Oh, look. If we go back to our, I forgot that I wasn't on the video here. Go back to there. So what I just did was 10.8 plus 3 is 13.8. 10.8 times 2 is 21.6, and I added 6 more to get 27.6, and if you look at what our answer to the question was, 27.6. So the answer to the second question is B2H6, because that one is the one that matched the molecular weight that we had from our calculation. All right, that's the end of this first video on variations of the ideal gas law. There's going to be another one. My video is getting too long, so I need to stop it, and we'll upload this one in a few minutes.